Hello my geniuses, welcome to another physiology playlist today. It's your great science tutor Lorenzo, and I'll be talking about the electrical activities of the heart. So I've done the introduction to the cardiovascular system. I've done the cardiac cycle, so I'm doing the electrical activities of the heart. How does the conducting fiber generate action potential and spread it out to the contracting fibers, which is the atrium and the ventricle. So we want to look at the ionic basis of the nodal cells, the ionic basis of the ventricular cells. We want to explain the electrical part of the heart, how the heart generate or it generate and how it contract, and let us know how to pump blood to the rest of the tissue. So if you are just new to my channel, make sure to subscribe and turn on your post notification button so that anytime I drop any video, you'll be sure to be notified. If you want me to make a video for you, put it down in the comment section. I promise I'll make that video for you. So let us jump right into the video. So now we'll be starting with the introduction to what electrical activities in the heart. So we start with what we call the cardiac electrophysiology. So the cardiac electrophysiology is the process by which the heart generates action potential, transmit and conduct it to all fibers, and then utilize them for pumping action of the blood between the heart, the blood vessels, and the rest of the body. So cardiac electrophysiology, cardiac, which is the heart, electro, which is the electricity, and the physiology is the process by which all these things are occurring. So the process whereby the heart generate action potential, transmit, conduct it to the what, to all fibers, from the conducting fibers to the contractile fibers. And now, what is the usefulness of this conduction of action potential? For the purpose of what, pumping action of the blood from the heart to the blood vessels to the rest of the what, tissues. You get it now. Remember I said in the introduction to the cardiovascular system, I said the cardiovascular system is a system between the heart, the blood vessels, and the tissues, which is the target what, cell. And for the tissues to work efficiently, it needs oxygenated and nutrient containing blood to work efficiently, because the nutrient containing blood contains ions, and the ions we have is what you have: the sodium, which are electrolyte, sodium, calcium, chlorine. All these are electropositive and electronegative ion that the cell use to generate what we call membrane potential. So this is what we are talking about in this video. So cardiac electrophysiology, generation of action potential, spread it across to the tissues. The reason is to improve and produce what, blood to be pumped out from to the rest of the tissues. Now what do we do now? We have types of cardiac cells. So we have types of cardiac cells. You have the cardiac muscle cells and you have the cardiac nodal cells. We have the cardiac muscle cells and we have the cardiac nodal cells. So that's what you have to know. We have the cardiac muscle cells, we have the cardiac nodal cells. The cardiac muscle cells are the contractile cells, which I talked about in my introduction to cardiovascular physiology. The cardiac muscle cells, they are contractile cells. I told you they are striated. So their fibers are crossing each other. So they are not like skeletal muscle fibers that are parallelly placed with their nucleus at the base. But this one, they are what? They cross each other with their nucleus at the center, and they have what we call intercalated discs. So they are striated, which means they contain actin myosin and what, sarcomere. They also contain tropomyosin. They also contain troponin. They contain most of the contractile proteins, and they are striated. So always remember. So these are the muscle layer that improve pumping action. They improve pumping action of blood from the heart to the vessels to the body tissues. And you get me? And they are the one that responds to what, electrical impulses that is conducted to the heart. So where are they located? They are located in the myocardium. They are located in the where? Myocardium. Don't always forget, they are located in the myocardium. This myocardial layer now, it is a cardiac muscle layer. Are you getting me now? It contains striated muscle fibers. And these striated muscle fibers contain intercalated discs, so that there will be spread of action potential to them, to all the muscle tissues, so that they can contract uniformly. So this is the cardiac muscle cell. The nodal cells, they are the specialized conducting cell. Their action is to generate action potential. Their work is to generate what? Action potential. How do they generate action potential? When a ligand, which is a hormone, like especially epinephrine, binds to them, because the epinephrine receptor is located on the SA node of the heart. So when epinephrine binds to them, or any other excitatory neurotransmitters, when it binds to the heart, are you getting now? So what does it do? If it binds to the SA node, what happens? The SA node generates what we call action potential. Are you getting now? The SA node generate action potential. So when it generates action potential, it spread it to specific pathways. When it spread it to specific pathways, this lead to what we call coordinated contractions. So the SA node is the organ that generate action potential, spread it to specific conducting cells. Also, when it's specific to specific conducting cells, this lead to what we call coordinated contraction. This lead to what we call coordinated contraction, and this coordinated contraction lead to what efficiency of pumping of blood. So it lead to efficient pumping of blood. So if I go back now, we have the cardiac nodal cells. What is the work of the cardiac nodal cells? They are the specialized conducting cells. Again, the cardiac nodal cells are specialized conducting cells. They generate and conduct electrical impulses. They generate and conduct electrical impulses. So they are specialized cells that generate and conduct electrical impulses. Are you getting now? So when they generate electrical impulses and pass them and transfer them, they transfer them into the contractile cells. The contractile cells is what we call the cardiac muscle cells that contains the atrium and the ventricle. They contain the atrium and the ventricle. So the cardiac muscle cells contain the atrium and the ventricle. So the action potential is generated from the cardiac nodal cells. Are you getting now? So when they generate from cardiac muscle, they send it to the cardiac muscle cells for contraction. Now, one thing that you should know about the cardiac nodal cells, they exhibit what we call automaticity. They exhibit what we call automaticity. So what is automaticity? Automaticity is the ability for these conducting cells to generate their own action potential independently. So because later we're talking about different nodal cells where they are located and what heart rate they can produce on their own. Because naturally the SA node can produce its own heart rate on its own, the AV node can produce its own heart rate on its own, the bundle of hits can generate their own. So the ability for individual conducting cell to generate action potential is called automaticity. And they are called the pacemaker of the heart. They are called the pacemaker of the heart. The pacemaker of the heart because their work is to generate action potential. So recapping a little bit, we will know that the heart has its own electrical system which generates and conduct impulses. The heart has its own electrical system which generate and conduct impulses. And it has what we call specialized conducting cells, which is called nodal cells. And what does the nodal cells do? They initiate and spread impulses. They initiate and spread impulses. And these impulses lead to what we call a coordinated contraction and efficient pumping of blood. They lead to coordinated contraction and efficient pumping of blood. So now we want to look at the conducting cells now. We want to look at the conducting cells one by one. So the first one we'll start with is what we call the SA node. The SA node is called the Sinoatrial node. The SA node is called the Sinoatrial node. So look at your screen. The SA node is called the Sinoatrial node. So it is called the natural pacemaker of the heart. It is called the natural pacemaker of the heart. So most ligand, most hormone have their receptor on the SA node. So when they bind to the SA node, what do? They can either increase the action potential generation in the SA node, or they decrease the action potential on the SA node. It's either they are increasing it or they are decreasing it. So it is called the natural pacemaker of the heart. Number one, you should know that. And where is it located? It is located at the right atrium. It is located at the right atrium, at the entrance of the SVC, near the crista terminalis. It's located at the right atrium, near the entrance of the SVC, which is the superior vena cava. Also close to the crista terminalis. And what is his work? His work is to initiate electrical impulses. Initiate it by generating electrical impulses, set the heart rate and rhythm of the heartbeat, set the heart rate and rhythm of the heartbeat. Also impulse spread through the atrium, causing atrial contraction. So when they generate action potential, they set the rate and rhythm of the heartbeat. So after generation, and when they do, they spread it to the atrial muscles. So they spread it to the atrial muscles. So the atrial muscle contract at the same time. But as the atrial muscle is contracted at the same time, what happened? The ventricular muscle is at rest, because I told you that they cannot occur at the same time. The atrial contraction of musculature or the atrial musculature contraction occurs at the same time due to the stimulation of the SA node. You get it now? So now the SA node can generate up to 60 to 100 beat per minute. 60 to 100 beat per minute, but some materials and textbooks will say between 60 to 80 beat per minute. But the highest it can go, it can be between 60 to 100 beats per minute. About the pacemaker activities of the SA node now. The SA node simultaneously depolarize. So when it simultaneously depolarize, impulses spread around the atrium, which I've talked about. Atria contract and pump blood into the ventricle. Remember I said the atria gets filled first. When the atria gets filled first, what happens? The SA node is being stimulated. So when the SA node is being stimulated, what happens? It contracts and push blood into the ventricle. Are you getting that? So when it contracts and push blood into the ventricle, the action potential is now collected, or the action potential that was generated in the SA node go around the atrial musculature and go to the AV node. Are you getting now? So now when the SA node fails, to generate action potential, the next power goes to the AV node. It's either it goes to the AV node or it goes to other conducting fibers. Are you getting now? So don't forget, SA node simultaneously depolarize, spreading the action potential it has generated to the atrial musculature. Then when it's ready throughout the atrial musculature, the atrium contracts at the same time, pushing blood into the ventricle. Then what happens? It goes to the AV node. I get it now. And when the SA node fails, the AV node and other people takes the next step. They are the one that cannot generate, they will not become the pacemaker of the heart. Now the next one is AV node. So what is AV node? We call it atrioventricular node. Are you getting it now? It acts as a relay station. What's a relay station? Action potential from the SA node moves to the atrium and converges at the AV node. So it acts as a relay station because it receives action potential from the SA node and transmits them to the bundle of His, or the His bundle. Because I tell you that the conducting fibers are the SA node, AV node, bundle of His, and we have the Purkinje Fibers. Are you getting now? We have the SA node, we have the AV node, we have bundle of His, and we have the Purkinje Fibers. So since you have understood this pattern, so immediately it gets it from the SA node. Are you getting now? It gives it to the AV node. So the AV node is our relay station that connects the SA node to the bundle of His. So where is it located? It is located at the upper part of the interatrial septum. Are you getting now? At the upper part of the interatrial septum, close to the tricuspid valve. So it is close to the tricuspid valve at the upper part of the interatrial septum. The interatrial septum is the septum that separates the right atrium and the right ventricle. So it's at the upper part of the interatrial septum, close to the tricuspid valve, close to the tricuspid valve, and we call that place where it is called the triangle of notch. The triangle of notch. The triangle of notch is where the AV node is located. I get him now. So what is the work of the AV node? Don't forget, the work of the AV node is that it receives action potential from the SA node. I get him now. It receives action potential from the SA node, and when it receives, it delay it slightly. That's what we call the AV nodal delay. When it receives it from the SA node, I get him now. It delays it for a small time. When it delays it for a small time, I get him now. It transmits it to the bundle of His. I get him now. It transmits it to the bundle of His. Why it is delaying is that as the atrium is contracting, it doesn't want the ventricle to contract at the same time. That's why there's a delay. So the atrium is contracting, the ventricle has to wait. Then when it's ready to the bundle of His, the ventricle cannot contract. The SA node allows the atrium to contract, the bundle of His allows the ventricle to contract, while the AV node just acts as a relay station that delay contraction of the ventricle, so that the ventricle will not contract more than the atrium. You get him now? So don't forget, it acts as a relay station of impulses before impulses is transferred to the bundle of His for the contraction of the ventricle. I get it now. So it can generate at least 40 to 60 beats per minute. I get a 40 to 60 beats per minute, or sometimes it can generate up to, let me say, at least 60 to 80 beats per minute. Some textbook, why some textbook 40 to 60 beats per minute. I get him now. And I tell you that when impulses arrive from the SA node, they are delayed for about 0.1 seconds. So I call it the AV node delay. So they are delayed for about 0.1 seconds. So that 0.1 seconds give time for the atrium to contract. It gives time for the atrium to contract before the ventricle. So that 0.1 second is called AV nodal delay, which prevents the ventricle from contracting when the atrium is contracting. So it delays for a while. That delaying is to what? To be able to give the atrium time to relax for the ventricle to not contract. So that's what we call the AV nodal delay. So all impulses from the SA node to the AV node have a delay of 0.1 seconds, which we call the AV nodal delay. Are you getting now? So recapping this phase, I told you the SA node is a natural pacemaker, generate up to 60 beats per minute. The AV node acts as a relay station, which delay impulses coming from the SA node to the bundle of hits with 0.1 seconds, and this delay ensure the atria contract first than the what? Ventricle. And the ventricle can also is a backup pacemaker too, which can generate up to 40 to 60 beats per minute. So the next one is bundle of His. Are you getting it? The bundle of His. Now, or we call it the atrioventricular bundle. The bundle of His, or the atrioventricular bundle. So now, where is this one located? Where is it located? Are you getting it? The atrioventricular bundle is very simple. It is located in between the ventricles. It's located in between the right and left ventricles, located and in the interventricular septum. So located in the between the right and left ventricle, located in the fibrous part of the interventricular septum. So it's located in between the two ventricles. Now, only electrical connection between the atrium and the ventricle. Now, what happens now? When action potential is spread from the SA node to the AV node, it has to give it to the bundle of His. I get it now. It has to give it to the bundle of His. So when you give it to the bundle of His will not divide it into the right and the left bundle branch. After I give it to the bundle of His will spread it to the right and left bundle branch. Are you getting it now? Don't forget the right and the left bundle branch. The SA node give it to the AV node. The AV node delay for 0.1 seconds, giving it to the bundle of His located in between the right and left ventricle. Now, it is not time for the ventricle to contract, because the bundle of His ensures ventricular contraction, while the SA node ensures the atrial contraction. Don't forget. The atrial contraction, the ventricular contraction. All these things are corresponding with the ECG. So when I'll be talking about the ECG, I'll be giving you that same context, because SA node, when SA node allows atrial contraction, we have the P wave. We have the what? P wave. So when you give it to the AV node, there's a flat line there. I get it. That is why we have the PQ PR interval. We have the PR interval when you give it to the AV node. That delay causes a PR interval. I get him now. It causes a what? PR interval. So when you give it to the bundle of His, there's a depression in Q wave. I get him now. There's a depression in Q wave as it spread to the bundle branches. So when it gets to the bundle branches, at the apex of the ventricle, they have the R wave. So we'll talk about it when you're in ECG, because I'll explain the ECG very, very well. So remember, SA node give it to the AB node. AV node does what? I give it to the bundle of His. The bundle of His spread it to the what? Bundle branches. Now, the bundle of His is only a normal pathway to reach from the ventricle. Are you getting that? If it is blocked, which means the ventricle cannot contract. If there's what, you have the right or the left bundle branch block. The right or the left, because the right bundle branch gives it to the right ventricle, the left bundle branch gives it to the left ventricle. So when there is a bundle branch block, which means it can be a right bundle branch block, showing you that the right ventricle will not contract. So when blood enters into the right ventricle, it will stay there. It will not pump out to the lungs. Thereby, there might be regurgitation into the right atrium. So if there is a left bundle branch, what happens? The left ventricle will not contract. And if it doesn't contract, there will be regurgitation into the left atrium. So now, one normal pathway to note is that the SA node is a natural pacemaker, generate action potential, spread it to the atrial musculature, give it to the AV node. The AV node is a relay center, delaying it for 0.1 seconds, giving it to the bundle of His. Bundle of His spread it to the right and left bundle branch. From the right and left bundle branch, it will go to the next one, which is the Purkinje Fibers. Remember, the right bundle branch can be blocked and the left bundle branch can be blocked, depending of any ectopic abnormality that occurs in the heart at that particular point. And they can generate, the bundle of His can generate action potential on its own for about 20 to 40 seconds. Sorry, 20 to 40 beats per minute. Are you getting that? So that is when the SA node has failed and the AV node has failed. Now, the Purkinje fibers is the next one. The Purkinje fibers, they are terminal branches of the conducting fibers. So after the right and left bundle branch enters into the ventricle to stimulate them, it gives tiny branches called the Purkinje fibers. Are you getting now? So they are arising from the right bundle branch and the left bundle branch. The right bundle branch gives the right Purkinje fibers. The left bundle branch gives the left Purkinje fibers. Are you getting now? So they spread from to the ventricular region. We call it the subendocardiac region. So they are going deep to the subendocardiac region. So they are arising from the right and left bundle branch. Are you getting now? Entering into the ventricle. I spread to what we call the endocardiac region. I get him now. So they conduct impulses rapidly to all the part of the ventricle. They conduct impulses to all the part of the ventricle. Why is the Purkinje fiber so important? They ensure the simultaneous contraction of the ventricular muscle fibers. Simultaneous contraction of the ventricular muscle fibers at once. Are you getting me now? So the right bundle branch brings action potential from the bundle of His to the right and left ventricle, but the one that ensures it to spread throughout the length of the ventricle is the Purkinje fibers. I get him now. So the Purkinje fibers carries impulses rapidly toward the ventricle, carries it from the right and left bundle branch. This result is a coordinated and powerful contraction of the ventricle, increasing the ventricular pressure. Now, blood is pumped efficiently into the pulmonary artery and the aorta. So the pulmonary artery to the right ventricle by the right bundle branch to the right Purkinje. So the right Purkinje fibers comes from the right bundle branch, allowing simultaneous contraction, pushing blood from the right ventricle to the pulmonary artery, while the left bundle branch from the bundle of His gives it to the left Purkinje fibers, and the goal is to do contract simultaneously, or contract the left ventricle simultaneously in order to push blood to the aorta. Are you getting me now? Now, one thing you have to know very important here is that conducting system, for us to overview it again, the SA node generates impulses 60 to 100 beats per minute, give it to the atrium. The atrial musculature contract, giving you a P wave. Now it gives it to the AV node. There's a delay in the AV node for 0.1 seconds, giving it to the bundle of His. The bundle of His spread it to the right and left bundle branch. So when it gives to the right and left bundle branch, then immediately the right and left bundle branch will generate a right and left Purkinje fibers. I get him now, giving the right and left Purkinje fibers. And I told you the right and left bundle branch can be blocked, causing the right heart block, or the right bundle block and the left bundle block. So key need to know: SA node is a natural pacemaker. AV node, there's a delay. The bundle of His generate normal electrical activity between the atrium and the ventricle, ensuring ventricle to contract simultaneously. The Purkinje allows the action potential to spread all around the ventricle. Are you getting me? Any defect to this pathway will either cause arrhythmias or heart block. Any defect to any part of the SA node, AV node, bundle of His, any of them will cause arrhythmias or bundle branch block. Are you getting me now? So very, very simple, very, very nice. So to repeat it again, we have what we call the mechanism of conduction of action potential. So I've said it 100 times. I've said this 100 times, but in this pathway I want to put some keynotes. I want to put some keynote here, especially the part in the atrium, which can come out in your big exams that you are writing. Are you getting me now? So again, what happens? Adrenaline binds to the receptor. It binds to the beta 1 receptor. So when adrenaline binds to beta 1 receptor, or we call it epinephrine, when adrenaline binds to beta 1 receptor, we call it epinephrine. What happens? Now it stimulates adenine cyclase. Adenine cyclase do increase cyclic AMP. Again, adrenaline or epinephrine bind to beta 1 receptor on the SA node. When it binds to beta 1 receptor in the SA node, it stimulates adenine cyclase. Adenine cyclase increase cyclic AMP. Are you getting now? So when you increase cyclic AMP, it opens the ion gated channel. Are you getting now? It's phosphorylating this pathway for the stimulating the SA node. Now the SA node will now produce action potential. So when it produces action potential, what happens? It spread it towards the atrium. It spread it to the atrium. So the atrium will contract simultaneously. So when it contracts simultaneously, it converges in the AV node. And when it converges in the AV node, there is a delay in the AV node, so that the atrium will contract finish before the ventricle will now contract. Are you getting now? Before the ventricle will contract. So this delay is very important, so that the atrium can push blood first and it settles in the ventricle, getting what we call the end diastolic volume before the ventricle will not contract. Because if there's no rest between the atrium and the ventricle, we have what we call arrhythmias, or the atrial fibrillation, or atrial flutter, any of the arrhythmias. So now, pathway through the impulse that travel to the atria. Now, what happens in the atria? So how do they generate in the SA node and spread to the atrium? So watch it now. So first one is the Bachmann Fibers. The Bachmann Fibers is one part. Now it's from the SA node to the left atrium. The SA node, for action potential to generate in the SA node located in the right atrium. The Bachmann Fiber is how action potential is spread from the SA node to the from the SA node to the left atrium. So first of all, action potential is generated from the SA node, which is located in the right ventricle, and for it to go to the left ventricle, it uses the Bachmann fibers. Are you getting that? So the Bachmann fiber, these fibers conduct action potential from the right atrium to the left atrium. They run in the anterior wall of the atrium. So the Bachmann fibers runs in the anterior wall of the atrium, and they ensure early activation of the left atrium, because after the right atrium have been contracted, or after the right atrium have been stimulated, it has to switch it to the left atrium to be Bachmann fibers. Now the next one is what we call the internodal tract. The internodal tract conducts action potential from the SA node to the AV node, because after it spread from the right atrium to the right ventricle, after the action potential in the SA node contract the right atrium, which is now spread to the left atrium, the next place it will have to go to the AV node. So in the AV node, the thing that carries from the SA node to the AV node is the internodal tract. In between the nodes, internodal tract, there are three tracts that conduct impulses from the SA node to the AV node. Are you getting now? There are three tracts that conduct it from the SA node to the AV node. They are located in the right atrium, and the three tracts are anterior tract, middle tract, posterior tract. Anterior tract, middle tract, posterior tract. The anterior tract is called the Tawara tract. The middle tract is called the Wenckbach tract, while the posterior tract is called the Torres tract. So there are three tracts that conduct between the SA node and the AV node. We have the anterior tract of Tawara, we have the middle tract of Wenckbach, and they have the posterior tract of Torres. Now the Wenckbach tract now. The Wenckbach is the middle internodal tract, which you talk about. Again, the Bachmann fibers carries it from the SA node to the left atrium. So the SA node will be stimulated, contracting the right atrium. We will put it to the AV node now. The SA node will be stimulated, contracting the right atrium, and is transferred to the left atrium to the Bachmann fibers. The next person now is the internodal tract. So after it stimulates the right atrium and the left atrium, it is now converges to the AV node to what we call the internodal tract. So we have three internodal tracts: the anterior, middle, and the posterior internodal tract. So the important one here is the middle internodal tract, which is the Wenckbach node. It is also called the middle internodal tract, and is a secondary pacemaker in the middle internodal tract. And the function is that it takes over the pacemaker when the SA node fails, because this will be important when I'll be teaching you about ectopic arrhythmias. So when I'm teaching you ectopic arrhythmias, it will be easy for us to explain this. Are you getting now? Very, very important. So now we have talked about the pathway that takes from the SA node to the AV node. You get it now? So don't always remember, SA node pacemaker send it to the Wenckbach fibers take it from the SA node right atrium to the left atrium. From there, the atria contracts simultaneously, giving it to the internodal tract. Internodal tract transfers the action potential from the SA node to the AV node. Are you getting now? So which part of the AV node? The middle part is the most important. So we have the anterior, we have the middle, we have the posterior. The middle one, which is the Wenckbach tract, is the secondary pacemaker, which is the most important of the three. So when they get to the AV node, there's a delay for 0.1 seconds. So now the next one we'll be talking about to finalize this one is the ionic basis for nodal cells and the ventricular cells. Ionic basis for nodal cells and the ventricular cells. Now this is very, very important for you to know. Ionic basis for the nodal cells and the ventricular cells. So very, very important. So I'll be doing this in my next video. I'll be doing this in my next video, so it will be very, very important, so you get it.